I just want to go over briefly how the moon was formed before we begin here. The moon, it's still not 100% known that this is how the moon had formed, but this is the best idea we have so far. Even comparing isotopes from the surface of the Earth with isotopes from the surface of the moon, where there's like unique chemical signatures, we've found that there's a similarity. So this theory seems to really work. So I'm just going to talk briefly about it. So back millions of years ago when the solar system was forming, and there was all this stuff swirling around and bumping into each other and causing collisions, there was a huge collision near Earth's orbit between two planets, a protoplanet and a smaller planet, which just a couple of days ago, in solar system news, there was they think that original smaller planet here, they think that was the size of about Mercury. So this wasn't quite the size of the Earth, the big one, it was smaller. This is about the size of Mercury. They combined, and there was ejecta coming. It's kind of hard to do. There we go. Still can't do it. There we go. Up, and then there we go. So there was ejecta coming out, and so in this region over here, there was all sorts of material that was floating around in space. Now behind me, you'll see millions of years. So now I'm going to go to the top view. This was just a crude drawing, and the reason why I didn't have it blue and green is because the land and oceans hadn't really settled yet. It was still a very hot surface at this time when this happened. And so actually there's a little bit of an interesting note here, is that this collision is believed to have sped up the Earth to its present rotation, which gives us our days. So it caused the tilt as well, which gives us our seasons. So we've got our tilt and our 24-hour day based on this collision, both extremely important for life developing on Earth. So now, let's go back to this millions of years thing. Millions of years pass by, and all of this ejecta out here is floating around near each other. Well, gravitational attractions pull those together, and the shape that is the best when you pull together, like what it settles on, it ends up being spherical, unless it's a really hard object, like a smaller object. So huge objects with lots of loose material will tend to form spheres. That's a little bit more complicated than we need to get into. So, without further ado, this is the top-down view. So now I've got the Earth from the top-down view. Now this is the axis of rotation. So this is the way the Earth spins. Okay, so all this material is also going in that direction as well. So what we'll see here is that moon follows along that direction because it was originally like this. So there's all this material up here. It's just a bunch of scattered rocks and dust and particles, and everything is just like still floating around here, and it's still coming together. Gravitational attractions are pulling the bigger blobs to the bigger blobs, and over millions of years, this ends up forming a sphere due to gravitational attraction. Now, just as a little side note here, H.G. Wells' Time Machine was one of the best books, philosophical sci-fi type books of all time, in my opinion, of course. And they made a terrible, terrible, terrible movie adaptation of it a few years ago. They made a couple of other movie adaptations of it, which are okay. But one of the things I did like about it, despite being completely destroying the philosophy and the story of it, was they actually had a section or a point in the movie where they looked up in the sky and they actually saw the moon in various chunks still in this forming stage, which I thought was kind of cool, but it's not realistic because humans wouldn't have been around yet. So that is how the moon forms, or how the moon came to be. This is why it goes in this direction, and this is why we have the Earth's tilt. This is why we have 24 hours a day, because it sped up the rotation. So we owe it all to this enormous cataclysmic event. Thanks to that, we get to live. There are really nice diagrams in textbooks and in various resources that draw the phases of the moon, which are very, very in detail, but the geometry can be really kind of hard to understand. So what I like to do usually is use this diagram, in which it kind of shows you how you would view the various moon phases from an observer on Earth. This is basically a top-down view of the Earth, so I am above the Earth looking down at the North Pole. The moon revolves around the Earth in this direction, the same direction as the axis of rotation, which happens to do with how the moon coalesced in the first place. And the Earth's revolution about the sun goes around this direction. So the sunlight I have drawn here, so the sun is over here. It's huge, it's enormous, it's very far away. But this is the sunlight coming from this side, and this is the various spots of the moon throughout the days of the cycle. So let's take a look first at the new moon. The new moon is usually not visible unless we have a solar eclipse. The new moon is usually not visible because the daylight is so bright that when the moon is not directly in front of the sun, which only happens in rare occasions, then the sunlight is so bright that you don't see the moon at all, plus the side that's facing you is not lit. Now, the moon is tidal locked, so we see the same surface. So let's just look at the full moon for a second here. All the features we're used to seeing of the full moon is one side of the moon that is facing us, okay? It's facing us at all times. There is no such thing as a dark side of the moon. The dark side of the moon really refers to the portion that we don't see facing us. So we see the same face of the moon all the time. So even though in this sense we are only seeing, this is going to be the same face as that, the same face as that, the same face as that. Here, when we get to the new moon, the dark side of the moon that we talk about, the side we don't see, but we've taken photographs with satellites and stuff, this happens to be fully lit. So if I'm on the dark side of the moon and I am standing there in a new moon, I am completely surrounded by daylight. Conversely, if I'm on the side of the moon that faces us, I am surrounded by nothing but darkness. So let me talk about how you view this on Earth. So an observer's line of sight to this moon from this position is straight this way. If I take this ruler and I cut off perpendicular on the moon, so I got a line coming here, this is perpendicular, this is what I see. I see just the shaded side of the moon. I see no light coming from the moon. That is a new moon. That is what we call the beginning of the moon cycle. It's like 29 and a half days or something, and we usually just say 28 because it's easily divisible by 4, so it's easier to understand. So we say the new moon starts at 0 days. All right, so I'm going to go on to the next position here. So this is a couple of days later, maybe 3-4 days later, and I'm an observer on the Earth, and again, my line of sight is like this. So I put my ruler perpendicular to that line of sight, and what I see is a sliver of light and a lot more shading. This is what we get a crescent moon, so we only see like a little portion of the light on that moon from this angle. So a couple of days later, I get to about 7 days through the cycle, and again, I'll draw the line of sight from Earth is coming to the moon here, and I'll put this ruler perpendicular so I can see what I see, the half that I see. And one half is lit and the other half is shaded, so we get a half moon. Now, we call this the first quarter moon because we're breaking the moon into a cycle of 7 days. So this is a quarter of the way through the cycle, even though what you view is a half moon. So when we see a half moon, it's really in its first quarter cycle. The next position, we go here and then do again, same thing, perpendicular to the line of sight, and a lot of the moon is lit, and just a sliver is shaded. This is what we have a gibbous moon. So we're on our way to fully lighting the moon. So we went from no light, a little bit more light, a lot more light, a lot more light, and then finally we get to halfway through its cycle and we get to the full moon, in which we see this whole side illuminated. The shaded side is away from us, the lit side is facing us. So this is halfway through the moon cycle. This is when the moon is on the other side of the sun. Remember, the sun was over here? Now the moon is on this side of the sun. In the new moon, it was in between the sun and the earth. And the full moon, it's on the other side of the earth, and the earth is in between the sun and the moon. So continuing on now, we've got this thing fully lit. We've got the moon fully lit, and that's our full moon. Now I'll go to this next part. And again, straight from the line of sight. And I put a line perpendicular. This is the half that I see. This is the half that's tidal locked that we see all the time. And I get more light than shadow, so I get a gibbous. So it's not full, but it's not half yet or less than half yet. So this is a gibbous moon. Now I'm getting less light because as I go towards the new moon again. So from the line of sight here, what I get is the other half moon in the cycle, and that's during the third quarter. So I see half the moon lit, half the moon shaded. And now we're going to go back to the crescent position, line of sight, perpendicular, just a tiny little sliver is viewable to me, and that's how I see a crescent moon, and most of it is shaded, and we get back to the beginning of our cycle. Now, what I want to talk about here is as I said before, the sunlight, this is the new moon only occurs when it's daylight out. All right, so you'll see crescent moons more towards the daytime than you will at night. You won't really see crescent moons late at night. Okay, the quarter moons also occur during daylight hours mostly, and only a little bit at night. Because it's lit for most of the time. The Earth is half shaded, half lit. So you start to see it near the sunset and or around the sunrise. One thing to look at is this line of sight. If I'm looking this way from the Earth, I'm looking towards the moon. The lit half is on my right side. The dark half is on my left side. Okay? So I know what quarter it is. If I look up at the moon and I see half the moon is lit, but I see it on the right side. If I look up and I see it on the right side, I know it's the first quarter moon. If I look down here from this point of view and I look down at the next point in the cycle, my point of view is this way. So now I'm facing it. So now the right side, the right side is dark. You can see that. The right side is dark. And now my left side is lit. So if I see the left side of the moon lit on a half moon, I know it's a third quarter. And the same goes for crescents. The same goes for gibbous. All right, so let me talk about crescent and gibbous. Crescent, you probably are all aware of what a crescent moon is. They usually tend to look like this. So they have a little sliver like that. And they make for nice little cartoon drawings of people sitting on the crescent moon and stuff like that. So it's shaped like a crescent, which is why you call it a crescent moon. All right, so this is the first crescent, but now we're going to introduce some terms, waxing and waning. Waxing is when you're gaining more light, so you're increasing. I think it's a synonym for increasing. So when we're in this upper half, we start off with no light. Again, just to remind you, no light. So now we get a little bit more light, so it's increasing. The amount of light on the moon is increasing in that part of the cycle. So we call this one a waxing crescent. It's distinguishable from this one by another word, which I'll talk about in a second. Again, we're increasing light here, so we get to a half moon. Then we're still increasing light, so the moon's getting brighter each day that passes as we approach the full moon. So here we get a gibbous moon. And hopefully I'll spell this right. I always spell these wrong whenever I get hopeful about it. A gibbous moon, okay, that's when we're in between a half moon and a full moon. So there's more light than a half moon, so there's more light than shadow, but it's not completely lit. That's a gibbous, okay? And this is increasing because it's getting lighter as the days go by. So waxing being the synonym for increasing, it's a waxing gibbous, okay? Now we're at the full moon. We're all very aware of the full moon. And now we get to another gibbous. So this gibbous here, more of it's lit than it's shaded. So it's a gibbous moon. It's on the left-hand side, so we know it's in between a full moon and the third quarter. So this is a gibbous, but now we're going to introduce a new term called waning. So when something's decreasing, it's waning. So the light is waning as we get to this point, because as each day that passes, less and less light illuminates the moon. So this is a waning gibbous. All right, so now we get less light. So we had a lot of it illuminated. Now we're to this point where only half of it's illuminated. This is the third quarter. This, we get to a different crescent, and this is called a waning crescent because the light's decreasing as we go towards the new moon. Okay, so now that we've got those defined, I want to point out something that's kind of handy to remember about waxing and waning. Okay, so anything, I'm going to draw a dotted line across this. I don't know if that's viewable on the video or not. Sorry to use the same color as sunlight. I'm limited by colors today in this room. So anything above this line, it's going to be waxing. So if the moon is on this side, remember it's traveling this way in its orbit. Maybe I should draw some kind of... So this is the way that the Earth is traveling in its orbit. Okay. So if it's on this side of the Earth, that's when it starts waxing. Okay, so above this line on this diagram is when it starts waxing, when it starts increasing light until it gets to a full moon. So above, this is all waxing up here. And try to really emphasize waxing, exclamation point. So everything up here is waxing. Everything down here, waning, waning. Everything down here is where the light's decreasing. And again, referring to waning. Referring to where it is in Earth's orbit. When it's on the side in the direction of Earth's revolution around the sun, that is when we get the waning phases of the moon. So this is a pretty handy tool to deal with, to understand kind of what you see as far as the moon phases go. And I want to point out just one more thing here. So if I draw now a line this way, oops, I should be through there. Let's adjust this. See, I'm not an artist. All my drawing comes from doing math and physics and astronomy and stuff. So if I draw a line straight through and I separate now into this half, you'll notice that the crescent is on this half. This is the half that is in between the Earth and the sun. And on this side is where we get the gibbous and full moon. And this is on the half that's on the other side of the Earth from the sun. So when the moon is passing that point where it's on this half away from outside of the sun's or the Earth's orbit line, if you'll call this the orbit line, then this is when we get, so that's when we get the gibbous moons. And the crescent moons are when it's sort of on the side of where the sun is. So hopefully that can kind of help you make sense of why you see the different moon phases and be able to identify them when you see them. For the fun of it, I'm going to try to demonstrate a solar eclipse. So say this is the sun in the sky, this circular part here. Say that's the sun in the sky. And say this is the moon. Remember when we scaled the Earth to the size of a basketball and found the moon was the size of a tennis ball in the lab introduction? Well, this would be the moon passing in front of the sun on an eclipse. Now it has to align just perfectly, but the moon casts a shadow just in a narrow band on Earth, just enough to cover the sun. And that's how you get an eclipse and you see the corona of the sun. Eclipses are rare events. The reason why they're rare is not really common knowledge. It has to do with the fact that the moon's orbital plane, as it goes around the Earth, is tilted with respect to the plane between the line of sight and of the Earth and the sunlight. So this gets really complicated. If I was teaching an astrophysics course or something, maybe we would get into the geometry of this, but I just want to point out that it's there. Why every time you have a new moon you don't get an eclipse, why every time you have a full moon you don't get an eclipse. So during a new moon you get a solar eclipse, which we'll talk about in a second. During a full moon you get a lunar eclipse. Why wouldn't that occur every time? Well, that happens to deal with the orbital plane of the moon, which is actually tilted 5 degrees with respect to the line of sight from the sun. So there's a lot of complicated things going on here. So if I were just to draw that line going towards the sun, it would be above or below, and depending on what time, sometimes it actually matches up, and it happens to be when it matches up with the ecliptic, which is a whole other plane. So now we've got 3 planes have to coincide perfectly. So that is why eclipses occur rarely rather than frequently, because this alignment has to be perfect. So only from 2 to 5 times a year do you even have the possibility of getting an eclipse. And for a solar eclipse, you have to be standing at the right spot on Earth to actually see it. And for a lunar eclipse, you actually have to be on the night-hand side of the Earth to see it. So not always do you get to see an eclipse when it happens. Sometimes you got to be in the right time and the right place. Now I want to talk about now I want to take that, erase your memory, just know that it's there, and maybe if you get a trivia quiz question, you're on Who Wants to Be a Millionaire or something like that, and they ask you why the eclipses don't always occur, well, maybe you can be the lifeline for somebody, or maybe you can win $1 million. You can win $1 million with that question. So, you don't have to know that for a test or anything, but just be aware as to that sort of geometrical arrangement existing. That's all you have to do. Just put it in the back of your mind and enjoy it. So now I want to talk about what happens to cause the eclipse. So I had my really silly demonstration before with the tennis ball, and I guess it wasn't that silly, and that was a solar eclipse. So let's start with that. A solar eclipse occurs only on a new moon, only when those orbital planes line up, and with the ecliptic plane, everything has to align perfectly, and they only occur during a new moon. So I'm going to put up here solar eclipse, and in parentheses, new moon. All right. So what happens here is you got the sunlight coming from this direction. And just like I had the tennis ball hanging there, and my light that I was holding, that was the sunlight. It's going to then cause the moon to cast a shadow on Earth. So if I trace out the shadow, go with something like this. Should be a little bit better here. And so you get a shadow cast onto the Earth. And in this spot, right there, this tiny little spot, then you have a chance to see the solar eclipse. There's people who hunt solar eclipses and like to take photographs of it. There used to be big science laboratories, essentially, because it was the only way we could study the corona. Now we've got nice satellites up there and stuff like that. So it also was the first confirmation of general relativity, because the gravitational lensing was observed by the stars that were behind the sun, so we could see that the sun was bending. That's a little too complicated. I'll stop there with that. So just think about this. So there's a shadow cast on here. So if you're standing in this spot, and it might be actually a little bit bigger. This is not to scale. It might be a little bit bigger, but it's just a spot on Earth, just a spot in which you can actually see the solar eclipse. And so there are much more rare events for you to actually witness than the lunar eclipse, which most of you probably have witnessed. So let's go over to this side, where I'm on the full moon side, and let's try to get the distances at least somewhat. Well, it doesn't really. This is not to scale, so let's talk about when that happens. So I've got the shadow from the Earth, and the shadow from the Earth, this is when the moon, again, all the planes have to line up here. So not every full moon is going to have this happen, but this is when the moon is in the shadow of the Earth, which casts a much bigger shadow than the shadow here. So just fill in this a little bit to get the impression of a shadow. So you'd think, why isn't these two lines are too solid when I look at that in the picture? Why wouldn't there be why wouldn't it be completely dark on a solar eclipse? Well, the reason why it wouldn't be completely dark on a solar eclipse is because of how light scatters from the atmosphere. The atmosphere scatters light, is proportional to the frequency. We'll get into light later. But for shorter wavelengths, blue, which is blue light, it scatters a lot easier. For longer wavelengths, it can keep traveling. This is why I actually see sunsets that are red. We'll get into that later when we talk about light. But so all that really survives from this light that comes through the Earth's atmosphere is the red light, and you start to see that red lunar eclipse, the blood moon. So that is like for a perfect scenario eclipse, but there are also other positions in which this can happen depending on how that orbital plane is tilted. So you can also have where this is partially, and you see a partial eclipse. We just had one of those recently here. We just had one of these partial eclipses where only a spot on this moon was actually lit in red from our viewing angle. So that's like when it doesn't fully pass through the shadow, but it passes through partway from the shadow. So let's talk about how this occurs throughout the course of an evening. Now the moon rotates around this way. So when you start to see this, let's just take this as a snapshot, at time 0. This is a snapshot, right? So now we're talking about not at different positions at different times of year. We're actually talking about position throughout an actual eclipse event. So you start to enter this region, and so you start to get this side lit up. Then you start to get here in the middle. So this would be like the peak of the eclipse. This is the really awesome part. I don't know who saw last year's, but last year is you could see Mars and Jupiter in alignment. You could see Saturn off to the side. It was quite a spectacular event if you were lucky enough to see it. So as it comes out of the Earth's shadow, they've got fancy words like umbra and penumbra. Never been a fan of those myself, but hey, depends on your requirements and how silly you want to be. So as it comes out, so if I'm looking at this on Earth, and again, this is going to go back to the original lecture. If I'm looking at this on Earth, so this is the direction that the moon travels in the night sky, and it travels from west to east, which is rather odd to think about. But what you see is you see this half, which is the left half of the moon, start to get red first as it's passing through the chest shadow. Then it's at the full moon, or when it's in the full effect, fully in the shadow. And then when you get to this part, you start to see the right side, and it starts to slip out of that shadow and carry on its wayward way. So that's a brief overview of eclipses. You know what, I should just write here 1 second just to remind you. So let's get away from the sequential time here. Let's put this back in the perfect scenario here, a perfect eclipse. And just to remind you that this is during a full moon, and it's a lunar eclipse. I should be consistent with over there. Whatever, you get the idea. So the key difference here is basically the size of the shadow as to why you see one a lot more than the other. This one you have to be in the perfect location. This one you pretty much have to be at nighttime. So next time you see an eclipse, you'll understand that you're looking at Earth's shadow. And if you're lucky enough to see a solar eclipse, don't look at it with your bare eyes, otherwise you'll burn out your retinas. Use some kind of pinhole telescope or something like that. But if you're lucky enough to see a solar eclipse, you'll know that you're really lucky because that shadow is tiny.